Okay, now we will discuss about the tautomerism. What is tautomerism? What is tautomers? If monovalent atom in the molecule or in the compound oscillate between two polyvalent atoms, then this type of isomers will be formed. These isomers are called tautoisomers or tautomers. This phenomena is called tautomerism. Okay, here you see I have take one example. You see here, this is the functional group. The carbon which is adjacent to the functional group is called the alpha carbon. If that carbon contains hydrogens, that hydrogens are called alpha hydrogens. So these are the alpha hydrogens. This carbon is called alpha carbon. Alpha carbon. Okay. So here this monovalent atom, that is proton, oscillate from here to this polyvalent atom, that is oxygen. At the same time this bond shifts to from here to here. Due to that reason, because of that, here this keto group converted to change to alkali group. This single bond converted to change to double bond. Okay. Then these two are the tautomers. This phenomena is called the tautomerism. What happened here? This is the monovalent atom. These two are the polyvalent atom. This hydrogen, this proton, oscillate between these two. Once it is here and another time it is here. You see here. This proton, if it is at O, then it will change to OH. If it transfer to here, then it will come. So between these two compounds there is equilibrium also. This is the equilibrium symbol. So this is changes to this and this changes to this. So this is the, so that this is a dynamic equilibrium. Dynamic means it moves to this, it moves to this. So this is called dynamic equilibrium. So tautomerism is also called as intramolecular. Intramolecular means in same molecule. In same molecule this proton is oscillating or this proton is transferring. So intramolecular proton transfer isomerism, and another name is dynamic equilibrium isomerism, because between these two compounds there is dynamic equilibrium. So this is called as dynamic equilibrium isomerism also. Okay, that's now. And another thing also we can observe here, that is this is the keto group, it converted to alkali group. These two are the isomers, same molecular formula. So these two compounds are called as functional isomers also. So this compound exhibits tautomerism and a functional isomerism also. Suppose in the examination it gives like that. They have given this compound and this compound exhibit which isomerism they will ask. Then how we have to give the answer? Then you have to follow this order, this preferential order. What is RT, M, FM, CP? This is ring chain isomerism, tautomerism, functional isomerism, metamerism, chain isomerism, positional isomerism. If that compound has two isomerisms, then we have to give the first preference according to this order. Suppose you take this compound, this has functional isomerism and a tautomerism. Then if it was given in examination, it will be given in examination, then you have to put the answer for, we have to give the preference for tautomerism. ఈ కాంపౌండ్ ఇచ్చి ఇది టాటోమెరిజం ఎగ్జిబిట్ చేస్తుందా, ఈజ్ ఇట్ ఎగ్జిబిట్ టాటోమెరిజం ఆర్ ఫంక్షనల్ ఐసోమెరిజం, లైక్ దట్ ఇఫ్ దే విల్ ఆస్క్, దెన్ మనం ఏం సెలెక్ట్ చేయాలంటే టాటోమెరిజంని ఎగ్జిబిట్ చేస్తుందని చెప్పాలి. ఇఫ్ ఇట్ ఈజ్ మల్టీ కరెక్టెడ్ ఆన్సర్, దెన్ యూ హ్యావ్ టు కీప్ ద బోత్ ఫంక్షనల్ ఐసోమెరిజం అండ్ టాటోమెరిజం. ఇఫ్ that is a single type answers, then you have to choose the tautomerism only. Okay, next one. Tautomerism exhibit cheyalante ఏ conditions are, which conditions are need for exhibit the tautomerism, you see here. Okay, so the compound should have the alpha carbon and alpha hydrogens, and that alpha carbon should be in sp3 hybridization. That conditions need to exhibit the tautomerism. Okay, if you observe this compound here, once you check that conditions, is it exhibit or not, you see here, this is the compound, this is the functional group, the carbon which is adjacent to the functional group is called the alpha carbon. This is the alpha carbon. This alpha carbon, what is the hybridization of this alpha carbon? How we can find the hybridization? If that carbon contains all single bonds, then it is sp3. Okay, now it has double bonds, then sp2. It is triple bonds, then sp hybridization. Here you see this carbon has all single bonds with these 3 hydrogen atoms and with this. So this is the sp3 carbon. Simply, this alpha carbon is sp3. Is it has hydrogens or not? Yes, it has hydrogens. So these hydrogens called alpha hydrogens. So this compound has sp3 carbon, sp3 alpha carbon, and it has alpha hydrogens also. Then it exhibits the tautomerism. Already I have written here, you see here. Okay, next. This is the acetone. Common name is acetone. IUPAC name is 2-propanol. Okay. Here, now we will check conditions for the tautomerism. First condition, is it alpha carbon or not? You see, this is the functional group. This is the adjacent carbon. So this is the alpha carbon. Next. Is it in sp3 hybridization or not? Yes, it is in sp3 hybridization. All bonds are single bonds, so it is sp3 hybridization. Next, is it have hydrogens or not? Yes, it has Okay. Now let us see the example of acetone. It has alpha carbon and it is sp3 hybridization, and it has, this compound has alpha hydrogen, so it exhibits the tautomerism. That is the compound this. Okay, and we will see another example. You see, this is the another example. This is the example. You see here, this is the functional group. First we will check the conditions for the tautomerism. This is the functional group, this is the alpha carbon, but this alpha carbon is in sp2 hybridization. This also alpha carbon, this also in sp2 hybridization. So it not exhibit the tautomerism. It not exhibit tautomerism. Now you see this compound. Okay, cyclohexanone, this compound. This is the, now we will check conditions. This is the functional group, this is the alpha carbon. So alpha carbon, it is sp3 carbon and it has hydrogens. That means this compound has the alpha hydrogens. So it exhibits the tautomerism. Okay, now how it exhibit, you see, this is the dynamic equilibrium. This proton shifts to here, this bond shifts to here simply. OH double bond, like this. And you see, this is another example. Here there is no alpha, there is alpha carbon, but it is not in sp3 hybridization. That's the point. This is sp2 hybridization, and this carbon is in sp3 hybridization, but there is no hydrogens, and that means there is no alpha hydrogens. So this is also not exhibit tautomerism. And you see, here sp2 carbon, here also sp2 carbon. So this is also not exhibit tautomerism. Okay, na? And I will write another example. You see, this is the butenone. Okay, na? Cyclobutene, butenone. In group undi, it has in group and keto group also. Here it is sp2 carbon, alpha carbon is sp2, here alpha carbon is sp3, and hydrogen is also there. Then it convert to like this. Here hydrogens are there, na? This hydrogen shifts to here simply. Okay, this is OH, this double bond shifts to here, double bond. Already it has double bond here, but this is anti-aromatic compound, anti-aromatic compound. So it is highly unstable. So this compound will not form because it is highly unstable. That means it is also not exhibit tautomerism. Okay, na? And I will take another example. You see, here I have written, once again I will write here. You see, this is C double bond O, C double bond C, CH3. Here hydrogen, here hydrogen. This also, just you put one hydrogen here. You observe this compound. It has alpha carbon, but it is in sp2 hybridization. You see, one double bond is there, so it is sp2 hybrid. But so that we thought it will not exhibit tautomerism. It will not exhibit tautomerism. But when these two are in conjugation, these two double bonds are in conjugation. Conjugation means alternative double bonds and single bonds are called the conjugation. Double bond, single bond, double bond. So it is in conjugation. Then we have to go to fifth atom. 1, 2, 3, 4, 5. This is the fifth atom. This we have to check. Is it sp3? Yes, it is sp3 carbon. And it has hydrogens. Yes, it has hydrogens. It has hydrogens also. Then due to this conjugation, this double bond shifts to here, this shifts to here, this hydrogens oscillate to or transfer to this oxygen. Then CH2 double bond C, single bond C, double bond C, here OH, here H. Here one hydrogen need to for carbon. Here also one hydrogen. So this compound will be formed. These two compounds are the tautomers. This compound exhibit the tautomerism. Actually we thought that this compound can't exhibit tautomerism because of alpha carbon is in sp2 hybridization. But here conjugation, due to the conjugation of these two bonds, and another fifth carbon is there and it has hydrogens and it is in sp3 hybridization. Due to that reason, this compound will exhibit the tautomerism. That we have to remember. Okay, like this another compound also we will see. You see, cyclic compound we will see. You see this compound, this is the functional group, this is the adjacent carbon, this one, this is the alpha carbon. Alpha carbon is in sp2 carbon, this alpha carbon also sp2 carbon. So it will not exhibit, it can't exhibit the tautomerism, but it exhibits tautomerism. How? You see, then these two are in conjugation, yes, these two are in conjugation. Then you have to go to fifth atom. 1, 2, 3, 4, 5. This is the fifth atom. It has hydrogens, Okay, and this carbon, this corner means this is the carbon, these are the carbons. Okay, that's you know already. This has hydrogens and it is in sp3, all are single bonds now, sp3 carbon. Then it exhibits the tautomerism. How? You see, this bond shifts to here, this bond shifts to here, this hydrogen goes to here. Then there is dynamic equilibrium. You see, this is the OH. Here double bond will be formed. This double bond shifts to here, and already here one double bond. You see here, delocalization of the pi bonds, so it gets stability. Okay, na? This is the aromatic compound, so it gets more stability. So these two are the tautomers. It can exhibit the tautomerism. Okay, we will check another compound. You see, simple compound HCN, hydrogen cyanide, it is also exhibit tautomerism. H triple bond carbon triple bond N. This hydrogen simply shifts to here. Okay, na? Then C triple bond N here plus here minus, and hydrogen is here. These two are the tautomers. Okay, na? This phenomena is called the tautomerism. Another two examples are there. Okay, another example is, you see, amine and enamine. You see this structure. This is the amine structure. Here, this is the functional group. Okay, now this is the functional group. This is the alpha carbon. So here alpha carbon sp3 hybridization and it has hydrogen. Simply this bond shifts to here. This hydrogen goes to here. Then it will become double bond comes to here, and here N, hydrogen comes to here now, so NH2. This is in an enamine, simply enamine compound. So these two are also tautomers. And the last example, you see, C double bond O, you are seeing, okay, and CH2, C double bond O, CH3, CH3. This is the compound. Okay, here observe it. It is also alpha carbon. sp3 hybridization. This also in sp3 hybridization. This is also sp3 carbon. It has alpha hydrogens. Here also alpha hydrogen. Here also alpha hydrogen. Because of these two functional groups. So for tautomerism, which proton transfer to oxygen? That we have to find. Suppose this methylene, this group is called methylene group. This is more active methylene group because of these two functional groups. So due to that reason, you see here how it will convert. C double bond O. Wait, sorry. C. This hydrogen, this double bond shifts to here, this proton transfer to oxygen, then OH. This is CH3 only, and here it gets to double bond, and you see here this double bond O, CH3. You observe this compound. Here there is conjugation, double bond, single bond, double bond, and there is chance for hydrogen bond. You see here. So because of that hydrogen bond and the conjugation, it is more stable compound. So automatically it converted to this compound only. That means proton transfer from here to here, not this, and also here resonance structure also will be formed. That means delocalization of the 5 electrons also will be formed here. Here this double bond shifts to here, this double bond shifts to here, this proton transfer to here. I write here that structure you see. Okay, I am writing here. So see, double bond shifts to here na, double bond O CH3 same, here single bond C, here again double bond C, this proton transfer to here. So OH here, OH. This CH3 is common. Here one nitrogen. So due to delocalization of pi electrons, it gets more stable. So this compound changes to from here to here. These two compounds are the tautomers. This phenomena is called the tautomerism. This is about the tautomerism. This is about the tautomerism. Okay, thank you.